Okay, thank you and welcome to the final day of Intro to Modeling with Modeling Cell Signaling with MATLAB. So I hope that on the final day you'll be able to learn just a little bit more. Again, this is mostly to expose you to the concepts around modeling in cell signaling, such as like network motifs and modeling signaling pathways, and of course the chemical reaction networks. Okay, so I'll just start by sharing my screen so that we can see everything together. And today you'll also have time to finish up all the materials from yesterday and day one. If you still want some time to go over that, I'm here to answer any questions, but you'll have plenty of time. So just for the final day, we're gonna go a little bit more into signaling pathways and specifically into enzyme kinetics. So hopefully you'll like that because I personally, it's my favorite section. And then we're going to learn about one last thing that I'm like super passionate about. So yesterday we talked a little bit about autoregulation and some of the properties that come with it. And we started to see some interesting time courses. But today we're going to just kind of jump in a little bit into like the last thing I wanted to cover for network motifs and signaling. We'll take our break, and then we're going to talk about ultrasensitivity, which is one of my favorite topics. And then you'll have the rest of the time to just finish all of the problem sets, look at all of your solutions, make sure that you leave with a solution so that if you ever want to refer back to it, you have something that you can look at. Okay, so for today, we're going to, what I hope that you take from today's workshop is to be able to identify ultrasensitivity and its benefits, especially as it relates to signaling pathways, as well as model some simple enzymatic reactions, specifically Michaelis Mann. So we're going to go through a very nice example with Michaelis Mann. Okay, so last time, one of the questions that was brought up was, we're assuming in this simplistic form that once MAP kinase has done the job, it is sort of converted into the MAP kinase, which isn't really the case, right? What we're seeing is that the MEX, once the MEC is phosphorylated, then it can go through and phosphorylate MAP kinase. And it's then that MAP kinase can go through and phosphorylate the transcription factor. So it's not that the MAP kinase disappears, it's that it acts as an enzyme. It's doing a job, it's phosphorylating a different protein. So that's sort of what we're going to go over today. What some of these proteins in these involved signaling pathways can act as enzymes, or they bind and do something to, they bind to another protein. So it depends on the pathway you're looking at. But the famous one is the Michaelis Mann kinetics equation, where we have an enzyme and a substrate, and the enzyme and the substrate first have to collide and bind. And only after the catalytic reaction takes place do we get the enzyme that unbinds from the substrate. And now the substrate is the product, or P. It's something has been done to the substrate. So that is more realistic in terms of what is happening in a cell. When, for example, in phosphorylation, we would have the protein that needs to be phosphorylated binds to the kinase, and only once the kinase and the substrate are bound can the phosphorylation actually take place. And then once the enzyme unbinds or the kinase unbinds, then we would get the phosphorylated protein and an enzyme. So Michaelis Mann sort of can encompass those types of reactions that take place with this specific middle step taking place. First they have to collide and bind. So to get us in the habit of writing our own differential equations, let's just take, a few minutes to write out our equations. Let's do, 4 minutes. So how many equations will you have? You have enzyme, you have substrate, you have the enzyme substrate complex, which is the middle one, and you also have product. So you'll end up with 4 differential equations. So I'll give you 4 minutes to do it, and then we can do it together, or if we have questions, we'll go through it. So just take like 4 minutes to do it. Okay, I forgot to record, so I'm just gonna recap real quick. So we're just gonna go over the equation. So let me just start over. So all we're doing is writing the equations together. That way you can reference them in the future. Okay, so what are we doing? Okay, so let's start writing the equation for the enzyme. So the enzyme shows up here and here. This E is the one that's the ES complex. So it's not the species of just enzyme. Oh my goodness, that's an E. Okay. Okay, so if we look at the enzyme from the far left side, we are losing enzyme from that forward reaction, the one with K on. So we're losing from with the reaction rate parameter K on, and we're losing the enzyme. But every time that the reaction takes place, there's a substrate attached to it. So this is E times S, not like the complex ES. And we also gain the enzyme from the reverse reaction, the one with K off. And this one, like when we gain the enzyme, we get it from the complex ES. So I'm going to put it in parentheses to show that it's like the complex. It's another species. It's not E times S, it's ES. Okay. We also gain it. So plus, and now it's the forward, it's the K cat. Why did I start with enzyme? Okay. And we're gaining it from ES. I should have started with the substrate, but that's okay. Okay. And then there's no, like, there are no other enzymes that we haven't addressed. All right, now let's do the substrate. Okay, the substrate. Do you guys want to change colors? Maybe that'll make it. Okay. And if we look at the substrate shows up here only, right? Because the ES is the complex. It's not, like it's its own species. So for the substrate, we are losing it from the forward reaction, the K on, but every time that the substrate is there, it's attached to an enzyme. And we're gaining it from the reverse reaction, this one, the K off one. So we're gaining it from the complex ES. So I'm just putting it in parentheses to show that it's a different species. It's not E times S. Okay. Let's do the complex ES. So ES is only in the middle right here. So we gain the complex from this forward reaction, K on. And we gain it from E, and every time it happens, it's attached to a substrate. And we're also losing the complex ES from this reaction, the one with the K off. So we're losing, so that means we're going to have a negative K off, and we're losing the ES complex. We're also losing it from the reaction happening here, the catalytic reaction, the K cat one. So we're losing K cat with the reaction rate parameter K cat, and we're losing it from the complex itself. Okay, last one. Let's do the product. Okay, the product only shows up at the very end of the enzymatic reaction, and we're really just gaining it. All right, so we're only gaining it from the forward reaction K cat. So K cat, and we're gaining P from the complex ES. So only once the catalytic reaction has taken place do we get product. Okay, so these would be our 4 differential equations that represent the Michaelis Mann kinetics. Are there any questions about how you get those equations? Okay. All right, so let me go back to the slides really quick. Because you know what's happening next, right? Because that's the pattern we've been doing. Okay, let's get MATLAB to solve it. So let's take a few minutes to get, I've only simplified here. The only thing I've done is just combine like terms. So let's go ahead and get MATLAB to solve those. So we'll try, I don't know, for like 4 minutes or something, and then I can show you how I did it. Let's take a moment. Maybe I shouldn't pause. No, I'll pause. Okay, let me show you how I did it in MATLAB. So I just let K on, K off be whole numbers. The initial condition, I started with just 0.5 for the enzyme and the substrate. I think I have these in the other order for substrate and enzyme, and then nothing, like we don't start off with any of the enzyme substrate complex and none of the product, because I want to see what happens with the product. And then I put all the equations into the system of differential equations. We can change our time, but I just started with 10 for now. And then I'm just going to plot everything. I should make sure that it's running. Okay. So what we're looking at here are all 4 species. And this is just for 10 time steps. But if you add more time points, then it'll smoothen out, like it'll be a lot smoother. So the red is just the, I think it's backwards. Let me see. Yeah, the red is the substrate. Let me redo that. There we go. There we go. So the substrate is in red. So we start off with 0.5 and then we kind of immediately lose it. But the enzyme, we drop a little bit because it's all coming up into the green, which is the enzyme complex, but we don't lose it entirely. You know, the enzyme is still able to like bind and unbind and then come back and bind to more substrate, and then it unbinds from the complex and it's allowed to go back and forth. And so even when it is in a complex, you can always kind of like replenish back your enzyme. And the product is in blue, so eventually we get all of the substrate to be in the completely like catalyzed or in the product state. So you can play around with some of these parameters, like I think was mentioned earlier, where K off can be smaller than K on, but what happens if it's bigger? Like what kind of reactions do you see? So let's take a look. So to see slightly different behavior, where now we don't completely get all of the product, but if we increase the time, let's see, let's just do 50. Eventually we'll get there. So you can see that the product, the substrate converting completely to product is still possible, even if K off is a different value. But let's look at K cat. What if K cat were to be something small? Let me change this back to 1. Now you can see there's something happening with the overall look of the product function. So before it was in that hyperbolic state, format, but now it's a little bit more linear because the catalytic reaction is taking too long to actually happen, or like the probability that the enzyme substrate unbind into the enzyme product is now very small. So you can see that these 3 parameters alone can influence the steady state, the dynamics. So they're always worth looking at, and you can also look at different initial conditions. So what if we started with 10 micromolar of substrate? Oh, let me change KCat. I want to look at a different KCat. So now you can see even more interesting. Isn't that cool? Oh, I didn't have enough enzyme. So do you see how the enzyme is like way down here? So let's change the amount of enzyme. I mean, it can be equal or not. It's up to you. Whatever you want. Or whatever you're interested in looking at. So you can see now the steady state happens very quickly within like 5 time units. This is why I like enzyme kinetics, because you can be looking at what's happening to the steady state over time, which parameters are affecting that steady state, and how much product do you get depending on all these other different parameters in this system. This was just with 3 different parameters: K on, K off, and K cap. Okay. So any questions about how we do that in MATLAB? Anybody? You getting an error? Yeah. Okay. Let me handle that, and I'll be right back. Okay. So all of that, right? No, this is yeah. So you start off with a lot of substrate. So you should either increase your enzyme or lower your substrate, and then you'll be able to see some more interesting stuff. Okay, any other questions, especially like those of you online? Do you have any questions about getting your plots in? Okay, so let's keep going. Remove this. All right, so you saw some interesting plots that could look something like this, or something along the lines of this one. This one in particular started with 10 molar for the substrate. Okay, and this essentially brings us to the famous Michaelis Mann equation, which a lot of you might already be familiar with, which is a hyperbolic function. We have the substrate Km, which a lot of you might have already heard of before, and the substrate in the denominator. So what I wanted to do was actually go over the derivation. So I put in the slides, like for future reference, you can have all the steps here, but we're gonna go through them together. So let me switch screens really quick. 1 second. My pen's not working. Okay. Yeah, my pen's not working. Okay, so I just wanted to go through the derivation. Oh no, my pen's not working. Give me 1 second. Okay, there we go. All right, so I'm just going to copy. Okay, so we have the equations right here. So if we wanted to derive the famous Michaelis Mann equation ourselves, we would have to make a few assumptions. The first one is that we have a steady state for the complex. So remember that when you think about steady state, what you're really gonna forever hopefully think about is the derivative equal to 0. So that's the first assumption we're gonna make. The second is that there's conservation, that the total amount of enzyme is constant and the enzyme is either free or it's bound. You know, so whether it's free with the product, like it's free and like the, where is it, this part, it's free with the product or it's free with the substrate. But no matter what happens, there, you know, either the enzyme is free or it's not. And if it's not, then it's in this complex. So those are like the two big assumptions we're going to make. And we're going to use these assumptions to find the steady state for the complex. Sorry, no, to derive the Michaelis Mann equations. All right, so if we want to set the derivative of the ES complex equal to 0, I'm just going to copy it down from here. So we're going to take this part and we're just going to copy it down. So that means 0 is equal to K on times E times S minus, and I'm just going to simplify at this point. K off plus K cat times the complex ES. Okay. And we're going to solve for the complex. So a little bit of algebra. So I don't know how comfortable you are with algebra, but I'll just go through it because I learned to do things. I try to never skip steps. So if we're trying to solve for ES, then we're going to, I'm just going to add it to both sides. And I know that you guys can probably do this a lot faster than I can, but I'm just doing it slowly so that if you ever refer back, you have exactly what you need. So then this simplifies to K off plus K cat times ES is equal to K on times E times S. Okay, and then we'll divide by the K off plus K cat. That way we get the ES by itself. So the ES complex is equal to K on over K off plus K cat times E times S. Okay, now let's use the second assumption. The second assumption was that the total amount of enzyme is always going to be ES plus E, you know, either the free enzyme or the one that is bound to the substrate. And the reason why I want to do that is because there's an E here. I want to replace it. I want to replace it with that. So let's just, on the side here, let's just solve for E. So E is going to be E total minus ES. That way I can just replace it here. So now we have ES is equal to, and then K on over K off plus K cat times, and now we're just going to replace this. E total minus ES times S. You can probably see where this is going. We want all the ES's together. So this ES and that ES needs to go together. So we're going to have to distribute this chunk. So K on over K off plus K cat times E total minus ES times K on, K off plus K cat times the substrate. All right. Oh wait, substrate over here too. Okay. So let's add this one. Sorry, that's the complex, K on, K off plus K cat to both sides. Sorry. Okay. So then we get, when we add these up, what do we get? ES plus ES times, I think I forgot an S. There we go. Over K off plus K cat is equal to, and then on the left-hand side, we just have S times the total times K on over K off plus K cat. All right, and then on this side, when you combine the fractions like that, what do you get? We get K off plus K cat times ES plus ES K on times S all over the same thing. I feel like I went the long way about this. That's okay. Okay, we're close though. All right, so if we want to simplify, what does this simplify to? Oh, I forgot the S over here. We should probably get the S's together. Okay. So on the left-hand side, what we want to do is now introduce Km, which from, what is it called? From the equation, hold on. Substrate. Okay, so what we want to do is have Km, and Km is actually going to be K off plus K cat over K on. So I'm just going to bubble this in to simplify. And on the left-hand side, what we end up getting is ES is going to be the, oh, sorry, this is E. The total enzyme times, and then this is, if we do the inverse of that, and after combining with the terms on this end, we're going to get K, sorry, we're going to get S over S plus, and then the inverse of that, which would be Km. Okay, so that's just for a, sorry, for the, what's it called, the complex. But S, so this is the other assumption. Well, no, it's not really an assumption, but we do know that the total number of, like the total substrate exists in the total that we started with. Anything that is inside of the complex minus whatever is in the product, because the product is no longer the substrate and we don't want to double count it. But this wouldn't actually make any of the equations look nicer. So we end up making another assumption. And this is what the Michaelis Mann equations assume, that S, like the approximation for S, ends up just being the total substrate that you started with. So we have to make that assumption in order for the kinetics to make sense, or for the equations to not look so bad. Okay. Now here are a couple of notes. So if we have the total, like the concentration of the substrate be a lot bigger than the total concentration of the enzyme, then what we get for the product is that it approaches zero. Like we get closer to zero. If there's too much substrate, then the enzyme can't handle everything, especially at the initial stages of the reaction, like as the reaction is first starting out, then you're not going to really have a lot of product. So that means that for ES, for ES right here, if the product is, if the substrate, if the substrate is a lot more than the enzyme, then ES approaches this equation, E tot, but now S is, approximately the total substrate. So we're just replacing S with S tot plus the Km. But if we have the other way, where the enzyme is more than the substrate, then this product doesn't necessarily go to zero. Okay, and then the final part is we're just going to look at P prime, because that's what we want, right? We want to know how much product we get. So P prime, where was that? Where did I put that? So the derivative for P is just P prime is equal to just K cat times the complex, which we now have. So I'm just going to copy that down. K cat times the complex, which we now know because we just solved it. So P prime is now going to be K cat times, and I'm just going to rewrite all this. Okay, and one of the things that we have noted, or like that I've noticed, or that the Michaelis Mann reaction assumes, is that these two are sort of like just written together as a single parameter, which is that the V max that's in the famous equation. So they just get sucked up into the V max. But one of the things, because of the assumptions that we made, this is only going to be valid at start. So at the start of the reaction, or like this is essentially the initial velocity. That's just the initial velocity. And if we look at, let me go back to the slide really quick. And if we look at the famous reaction, that V max is represented by K cat times the total enzyme. And that is like the maximum velocity. And that's why this function has this sort of hyperbolic function where the Km can tell you a lot about the kinetics because it's made up of the K off, K on, and the K cat, which is why it's kind of hard to measure those biologically. And instead we measure Kms, Kms and Kds and all of that. Okay, so if you ever want to look at it on your own, I did include the slides here of the assumptions that we made. I just skipped the algebra, but you can still do it. I added in, the last assumption and then how we substituted into the product. Okay, so you're always free to look at it. I'm sure you could find it online as well. If you'd rather see something else, I can find a paper and add it in for you, but I just wanted to include the slides here if you ever want to see them in the future. Okay, so hold on. Are there any questions before we take a break? Okay, let's take a quick little break. Let me see, 2:25. So we'll come back at 2. I have here until, so 15 minutes. So from 2:25, we'll come back in 15 minutes. Where's my pen? So let me pause the recording real quick. Oh, I hope I was recording. I hope I was recording. Okay, one of the questions that came up was how do we plot the Michaelis Mann equation? So I'm gonna One second. I'm just going to plot it here. So the Michaelis Mann equation, let me just go back to it right here. V max S tot over Km plus S tot. So we would define V max. I don't know, let's just leave it something like that. Let me make a comment really quick. Plotting the equation. And in this case, the x-axis is going to be the S tot. So let's say we start from 1 and I don't know, all the way to like 100 or something. MATLAB can handle it. And then we would just write the equation. So now our P velocity is going to be V max times S over, wait, am I doing that right? Yeah, S tot over, oh, I didn't define Km. Km, let's say Km is 1. Km plus S tot. And then because this is, we want a value for every single S tot, so we're going to use the dot operator in MATLAB.
You know, to use Km, that's 2.5.
Sorry. Okay. And then to plot, I like to copy paste stuff. We're going to plot S tot versus P velocity. And I won't dash it, and I think I want it in black. And on the x-axis, we're going to have S total. And on the y-axis, we're going to have the P velocity.
It wouldn't be.
Okay. We'll try different values just so we can look. And the legend is basically just P. So let's make this figure 20. You don't have to go in order. I just have to do that. So you can see it's got that hyperbolic shape. Sorry. I'm just changing the legend because I want the tot to be, a subscript. Okay, and that's how we would plot the Michaelis Mann equation. I should change that to equation. And you can plot basically anything like that. And if you're interested in more realistic values of S tot, you can always change just the vector S tot. Okay, any questions about that? Let me look at the chat really quick. Or any hands raised? If you wanted to plot directly, yeah. A lot of times those two values are measured experimentally, or you can do fits. Like if you had a lot of data, you would just fit them back and extract out the V max and the Km. But we're not doing data fitting in the workshop, but maybe that's something we can do in the future. Put it in the evaluation. Okay. Okay, so we did this, we took a break. Okay, and now we're just, the last thing that I wanted to talk about, and this is probably gonna go relatively quick because I want you to have enough time for the rest of today to go through all of the problems and get the solutions to all of your problems. But let's talk a little bit about ultrasensitivity. So to talk about that, we should probably go over what cooperativity is. So, so when biologists talk about cooperativity, they usually mean one of two things: cooperative recruitment or multi-site cooperativity. But there's also synergy. So these are three different topics that kind of can be confused, or they go hand in hand. So for example, cooperative recruitment is sort of talking about like cooperative binding of transcription factors to DNA. Like if one transcription factor is bound to DNA, then more transcription factors will come and bind to that DNA. So that's like the cooperative recruitment. There's multi-site cooperativity, which is like hemoglobin or like an allosteric cooperativity. So in hemoglobin, it's a 4-site protein, and once one oxygen is bound, it's easier for oxygen to bind to the other 3 subunits. So that would be like multi-site cooperativity. But synergy refers to a combined effect, such that, for example, transcription factors, if only one transcription factor is bound to DNA, then you get an X amount of, transcription. But if more than one transcription factors are bound to DNA, then you get even more transcripts, but like not in an additive way, in a multiplicative way. So like the way that I like to think about synergy is about effect. So let's think about phosphorylation for a second. So when the modification of one site alone yields a certain response, for example, like given off here by the little bright, like the small amount of bright red, like the halo, there's a small effect if one site is phosphorylated, or if the second site is phosphorylated, you get probably something similar. So here, like you can kind of see it on a graph, like if the first site is phosphorylated, you get a certain amount of activity. And if only the second is phosphorylated, you might get a slightly different activity. But if both are phosphorylated, you get an extreme amount of activity, like here, where it's more than additive. Like if we added these two numbers and we stack them up, it would still be less than if both are together. So synergy refers to that, it's like the synergistic effect is usually multiplicative and not additive. And we actually see it in gene activation. So I just wanted to give you a different example where if we have just one one gene activator bound to the DNA, you get 1 unit of transcription. But if you have more, like in this case, if we have 4 transcription factors bound, then we get 500 units of transcription, not 4 units of transcription. So that is more than additive, it's multiplicative. And so synergy actually refers to that. While cooperativity, so I'm just going over it again. So cooperativity, let's think about it in terms of multi-site cooperativity. What that refers to is if we have one site modified, we can either get the second one to occur more, like the second one is more likely to occur, kind of like this big arrow means like the probability that the second one is modified is a lot larger, or you can even have negative cooperativity, in which case that means that the probability that you have one site modified, the probability of getting the second modified is even lower. So you could have negative cooperativity as well. So it goes both ways. In hemoglobin, which is the classic example for when people talk about cooperativity. So hemoglobin exists in 2 states, either it's active or it's inactive. The active state is the one that's more likely to bind to oxygen once the first one has been bound. The inactive state is in a 10th state, and it's less likely to bind to oxygen at any one of the subunits. So again, hemoglobin is made up of 4 subunits, 2 alphas and 2 betas. And that makes up hemoglobin. And what happens, so in Michaelis Mann, which is this green curve here, if we had measured the amount of oxygen on, if we have the amount of oxygen on the x-axis and on the y-axis, we're looking at the amount of hemoglobin saturation. If hemoglobin acted in a non-cooperative way, we would see a Michaelis Mann response, which is the green one. But what we actually see is the red curve, where a small amount of oxygen doesn't completely, fully activate hemoglobin, but once it passes a certain threshold, we see we see this quick response. So it goes from it doesn't respond if there's background noise, but once you get a certain threshold, then it picks up and then you get full activation of hemoglobin. And it's that switchness that we call ultrasensitivity. And the ultrasensitivity is that switch-like behavior in a response. So, and the Hill number is actually what we can use to measure ultrasensitivity. So like if you needed a number to tell you how ultrasensitive something is, we actually have the Hill number. And the Hill number, so one of the things that we do know about, is that when you have multiple modification sites or multiple, transcription factors binding to DNA, you can actually get these types of ultrasensitive dose response curves, like this one here, where after, before a certain threshold, you don't respond if there's not enough enzyme. But once you pass a certain threshold of enzyme, then we get like a quick response, and now your protein is completely activated. I think that's me. I think that's Slack. Okay, sorry about that. Okay, so ultrasensitivity is something that we can use to measure this type of switchness behavior, or the the sigmoidalness of the curve. For example, the ultrasensitive curve is more sensitive to changes in the input, which is what we saw in that curve, where at first it doesn't respond, but once you hit that threshold, it's going to quickly respond. Like the protein is going to be activated very quickly. So this equation here is the Michaelis Mann one that is less sensitive. But the hyperbolic one of the things that has been found is that you need at least an 81-fold change in the input to see an increase in the response. But if we wanted to just measure like how ultrasensitive something is, there has been a generalized form of the Hill number, which is given here, where we have the natural log of 81 over the log of the EC90 and EC10. And just to kind of remind us what those values are, the EC10 is the effective concentration at which there's a 10% output, while the 90 is the effective concentration at which there's a 90% output. So the ratio of these two would be, divided natural log. This would give us the actual Hill number. And all we have to remember is that a Hill number greater than 1 means ultrasensitivity. A Hill number equal to 1 means that you have no ultrasensitivity, or it's just a Michaelis Mann response. Okay, so what are some of the benefits of having ultrasensitivity? Well, if we look at the Michaelis Mann response in the dashed line here, which has a Hill coefficient of 1, if there's a little bit of change in, for example, kinase or the input, the protein is going to respond. It doesn't care how much there is. It's responding from the very beginning, because the initial velocity, which we had calculated, is always, it's always increasing. It's positive. So what happens if we have ultrasensitivity is that a protein won't respond if there's not enough kinase or enough enzyme or enough of the input. And that's a benefit, because you don't want to be responding if there's background noise of some transcription factor. You only want to respond if you mean it. And ultrasensitivity is one of those ways in which we can do that, because we have little response if there's noise or if there's not enough input. But there's a quick response, it's fast at responding once you pass that threshold. So the maximal response is reached quickly if we have ultrasensitivity, while in the Michaelis Mann, we don't have that. The change is not as fast. The change is gradual. And it's just to show, the red has the Hill number of 5. So you can see how ultrasensitive and how steep that curve is if you just have a Hill number of 5. Hemoglobin has like 2.7. Okay, so let's just practice plotting. This was basically the end of it. Just plot 3 different curves with the Hill equation. This is the Hill equation here. If you have different values of n, so include the Michaelis Mann one, which is an n equal of 1, and then try other ones. Like you can try 1.5, you can try 10, and you can try whatever you want. Just plot 3 different equations, or 3 different Hill equations that have a Hill number of 1 and higher. Or you can even look at a Hill number that's less than 1, and you tell me what you see. So let's take 5 minutes. Okay, so hopefully you were able to plot some of those. I can share some of mine. I think I plotted them all together. Yeah, so I did n is 1 in red, n is 2, 3, and we can even change it to 30, so we can look at them all together. You can see that there's a quick response for the n equals 30. And you can change around the k as well. Change around the plot a little tiny bit. You can do 5. This is 5. Oh, sorry, I forgot to add the n to all of these. There we go. You can see all the different plots here. There we go. So n is 5. You can see a much quicker response. 2, and you can change the number of points to give you a much smoother curve, which I haven't really been going over, but you can see how smooth that is now. And you can see that some of these have a very good threshold, and you can have a good switch, you know, how quickly it gets to 100%. Okay, well, any questions about plotting the Hill function? Let me check the chat really quick. Okay, well, the last, you know, I know we just got back from a break, so we can skip this part, but now the only thing left to do is to work on the problems from the problem sets. So for day 3, you know, we did some of these, but you are free to do all of these on your own. You'll get a little bit of practice, you know, with Michaelis Mann, so play around with the parameters and all of that. Although we kind of did that together, we did this one together. And then for today, you're going to have more practice with the Michaelis Mann and answer a few questions. And then this last network motif, where you're going to see 2 types of responses based on the type of function that you're putting in. And if you need help getting any of the equations in, you can raise your hand, unmute yourself, or ask me. I will be here until 4:30. And then the last one is it'll show you some very interesting oscillations if you have very Hill or high Hill numbers. So when you have high Hill numbers, you can see some very, very interesting curves. Like you'll see them oscillating, and it's super fun. And that's really all I have. So if you do not have to stick around, if you would like to be in a break room, I can put you in a break room with somebody else, or you know, whoever you want. You don't have to stick around either, and I will put up the solutions at 4:30, like my notebook, so that you can have access to them, into the Google Drive. And then I know that there's another Google Drive with the videos in them. I'm going to go ahead and just merge the 2 so that you'll have access to everything from here on out. But feel free to stay and work on these problems. And if you have any questions, I will be here to answer them. So I'm going to go ahead and stop sharing and stop the recording.